Hello, my name is Joshua Singh, and I will be giving a brief overview of our topic, Corporate Responsibility for the U.S. Air Navigation Service Provider, a decision support tool to reduce CO2 emissions from en route flights, which is a two-semester system engineering senior design capstone project at George Mason University. I had the privilege of working on this project with Adel, Elessawy, Gurpreet, Singh, and Karym, Zabara, and sponsored by Mr. Akshay Bele, representing the Center for Air Transportation Systems Research at George Mason University. Climate change is any significant change in the measure of the climate. The increase in population, energy demand, burn of fossil fuels lead to an increase in greenhouse gas emissions, which are gases that absorb heat from the atmosphere, leading to increase in global temperature. Therefore, climate change and some of its impacts, which include storm, floods, and drought. Aviation has a current contribution towards greenhouse gases of 3% globally and 3.63% in the United States. There is an increase in the demand for air travel, which is leading to a 2% annual air traffic growth, which is the increase in passengers and aircraft movement, which causes an increase in CO2 emissions. The aviation industry is operated by multiple enterprises, therefore it would be hard to hold one enterprise responsible. However, the industry needs to address its shares unselfishly to minimize the impacts on the climate, which leads us to corporate responsibility, which is corporations setting and implementing core values with positive impacts on the communities and society. Air navigation service providers are organizations that separate the aircraft on the ground or while in the air in an assigned airspace with a primary objective of safety. The ANSP controls the flight transit time, which influences the fuel consumed and emissions produced. Our problem is to increase in emissions accompanying growth in demand for air travel will prevent achievement of goals for emissions reduction. The Federal Aviation Administration, the ANSP for the U.S., has no current system to estimate emissions produced in its airspace, measure performance, and evaluate alternatives for emissions reduction. How can the FAA increase its performance? Even though airlines file flight plans for their own aircraft, they are restricted to airway routes which are not necessarily the most direct routes. For example, in a no-wind scenario, great circle distance routes would have the least transit time, therefore the least fuel consumption and emissions. However, in the presence of wind, the most direct routes would be the wind optimal routes. These routes cannot be implemented because of the current structure of the U.S. airspace and the fear of increasing the air traffic controller workload, who have to resolve conflicts between flights, which is a violation of separation standards. Our focus of work is to provide the FAA with a decision support tool to estimate emissions produced, track their performance, and make changes that will give the airlines more options when filing flight plans. Also, the focus of work includes an analysis of alternative routes, user-preferred routes, to evaluate their impacts on the ANSP's performance. There are a lot of flights flying in the U.S. daily. We decided to categorize flights based on the distance they fly. We divided them into 4 categories: short flights, flying less than 500 nautical miles; medium flights, flying 500 to 1,000 nautical miles; semi-long flights, flying 1,000 to 1,500 nautical miles; and finally, transcontinental flights, flying more than 1,500 nautical miles. As mentioned before, the suggested alternatives are user-preferred routes that we will be calling near-wind optimal routes, which involve the great circle distance routes, with the incorporation of the wind. However, we will be looking at different scenarios. First is status quo, which means all flights remain the same, flying airway routes, then implementing near-wind optimal routes for flights in one distance category at a time. For example, we will implement near-wind optimal routes for transcontinental flights, and the remaining flight distances, semi-long, medium, and short, will use the same airway routes. Then implementing near-wind optimal routes for flights in 2 distance categories. For example, near-wind optimal routes for transcontinental and semi-long distance flights, and airway routes for the short and medium distance flights. Then we implement near-wind optimal routes for flights in 3 or 4 distance categories. There are 2 major tools used in this project: Aircraft Emissions Decision Support Tool, AEDST, and Future Air Traffic Management Concepts Evaluation Tool, FACET. First, AEDST, which was designed by the team as a deterministic model using C++ to assist the FAA in estimating emissions and their airspace and to measure their performance. The tool has two primary sources of data. First, the Enhanced Traffic Management System data, ETMS, that contains filed flight plans and radar track data for flights on a given day of traffic. Second, the base of aircraft data performance files, BADA, provides the fuel burn rate of different aircraft types at a given altitude, velocity, and phase of flight, climb, cruise, and descent. For the baseline airway routes, the ETMS radar track data and the BADA serve as inputs into the AEDST. For the near-wind optimal routes, FACET, which is a simulation tool designed by NASA and used initially to simulate the Great Circle Distance route, outputs the track data for those routes given the route information extracted from the ETMS to serve as an input in AEDST. The FACET Great Circle Distance track data goes through a preprocessor in AEDST to incorporate the wind into the Great Circle data routes and make new data for the near-wind optimal routes. The outputs of AEDST given the provided data are the distance flown, transit time, fuel consumed, and CO2 emissions produced from individual flights in addition to the total fuel consumed and CO2 emissions from all flights together. FACET is also used to identify the number of conflicts that occur between aircraft, which is one way of representing the air traffic control workload, by utilizing the Great Circle Distance route information in the ETMS flight plan data. The figure shows the reduction in time, fuel consumed, and emissions in each scenario of the alternative configuration compared to the baseline case. The purpose of showing the transit time, fuel, and emissions is to show the direct relationship between them, so any of the three can represent the ANSP's performance improvement. As you can see, A1, which is implementing near-wind optimal routes only for transcontinental flights, provides the minimal reduction in emissions, which is 1%, while implementing near-wind optimal routes for all flights, transcontinental, semi-long, medium, and short-distance flights, provides the maximum reduction in CO2 emissions, which is 20%. Here is a reduction in fuel from flights in 1 day translated into fuel cost savings based on the current prices of fuel. Implementing near-wind optimal routes only for transcontinental flights provides the minimum fuel cost savings for the airlines with about $900,000, while implementing near-wind optimal routes for all flights provides a maximum saving of $16.7 million. As mentioned before, that the evaluation of the ANSP's performance would be based on the emissions produced and the ATC workload in each scenario. The emissions produced is the total emissions in each scenario, and lower is better. The workload is measured through the number of conflicts that air traffic controllers have to resolve between flights, and lower is also better. The importance of each measure was acquired through a survey on the subjects passed out to experts in the field. The table shows the ranked best to worst results of the ANSP's performance based on the measures explained previously. As you can see, the best scenario is implementing near-wind optimal routes for flights flying semi-long, medium, and short distances. Even though this scenario does not provide the most emissions reductions compared to the scenario with near-wind optimal routes for all flight distances, but the workload of the air traffic controllers is lower, and that's why the ANSP has a better performance. Also, implementing near-wind optimal routes for only transcontinental flights has the worst rank even compared to the baseline, because it increases the workload of the air traffic controllers compared to the baseline case. Finally, our recommendations. We recommend the designed aircraft emission decision support tool to be implemented by the FAA to estimate emissions in its airspace and measure performance. Implementing the tool shows the willingness of the FAA to act responsibly in a world becoming more aware of aviation's contribution to climate change and global warming. We also recommend to make the necessary policy changes to support the use of user-preferred routes to give airlines more options when filing flight plans. As shown in the analysis, that implementing near-wind optimal routes for flights flying semi-long, medium, and short distances increased the ANSP's performance by 19% in regards to CO2 emissions, provide airlines with fuel cost savings of approximately $16 million in 1 day of flight, and also reduces the workload of the air traffic controllers by 2.5%. Here is a list of our references. Thanks for listening.